Okay, so we have oh, last Tuesday, sorry. All right, so the proposition is to show that if x and y are two independent random variables, then their product has expectation, okay, and then it is equal to the product of their expectations, okay, so that and we have complete the proof of the first part when x and y are both non-negative random variables. Okay. All right. So now we will prove the second part that if x and y are arbitrary random variables but have finite expectations, then x times y has a finite expectation, and this finite expectation is again is equal to the product of their expectations. All right, so now x and y has, yeah.
Can you give an example of this statement? Can you give an example?
Example?
Yeah.
Well, okay. Okay, in the proof of the first part, we divided it into two steps. The first step is to show that if these two random variables are non-negative discrete random variables, okay, and so we have shown that specific by the definition that the expectation, because if x and y are discrete, then their product is also a discrete random variable. Okay, and so that the proof actually illustrates that this identity is true for any non-negative discrete random variables. So if you say that for discrete random variables, then that is the proof will be an explicit proof for any. So if any problem relating to non-negative discrete random variables, for example, if x and y are independent Poisson distributed random variables. Okay, and then in the proof for the first steps, we show that this expectation is equal to the product of the expectation directly. Okay. So, yeah. Okay, so I'm not so sure if that is a good illustration. For examples?
We are learning this property to apply it in some practical question, right? So there must be some example for this.
Oh, yeah. So it will be used, for example, if we study the correlation of two random variables. Okay? Because correlation is an important property in signal processing. And so if two, because of this identity, so we will be able to prove that the correlation of two independent random variables is 0. That is an application to that. Yeah. So correlation is a very fundamental concept. Okay. Yep. Okay, so this is a proposition. Even though it's a general result, but we can apply this result to data concept, which will be useful in applications, such as I say, the correlation. All right. Okay, so X and Y have finite expectations. If and only if okay, so X and Y has finite expectations if and only if the positive part of X has finite expectation, the negative part of X has finite expectation. Okay, by our definition of expectation in chapter 5. Okay, and the same, if Y has a finite expectation, but only if that the positive part of Y has finite expectation and the negative part of Y has finite expectation. So, all right, so the given condition, X and Y has finite expectations, means that these 4 expectations of non-negative random variables are finite. Okay, because they are all finite. Okay, so that X times Y, all right? So this is X plus okay, so we have, so the product of X and Y is actually a linear combination of these 4 non-negative random variables. Okay. Yes, please.
Expectation of X minus should be less than negative infinity?
Less than, yeah. Less than means that it is finite. Because the expectation of non-negative random variable always exists. By our definition in chapter 5, but the value can be infinite. Okay? Right, so by our definition of expectation of non-negative random variables in chapter 5. Okay, so the expectation always non-negative, but maybe infinite. All right? Infinite. And for a general random variable x, we define the expectation of x is the difference of the expectation of its positive part and it's the expectation of its negative part. Okay? Provided that any one of them is finite. Because if both of them are infinite, then the difference is meaningless. Okay? Right? So that the existence of the expectation of a random variable it depends on that one of the 2 expectations is finite. Okay, and the expectation is finite if and only if both of them are finite. Okay, that is the concept we learned in chapter 5. Okay. Other questions? Okay. Now, since x plus x minus y plus y minus are non-negative, okay, so we have expectation of okay. Okay, so by part 1, because in part 1 we prove the identity for non-negative random variables. So we have these 4 identities. Okay, and because each expectations here are finite, so their products must be finite too. All right, so this is a random variable with finite expectation. This is a random variable with finite expectation. This is a random variable with finite expectation. Okay, also this is a random variable with finite expectation. So now, by proposition, so by the linearity property, by the linearity of expectation in proposition 7.2.8. This proposition, I have asked you to prove it in the recommended exercise number 10, right? So, by linearity of expectation, x times y, which is has a finite expectation. Okay, so now we show the product has finite expectation, and its expectation is the same linear combination of the corresponding expectations here. Okay? So this is from proposition 7.2.8. Now we have this identity, so we have okay, and then this comes to be okay. So the sum of these 4 terms is equal to a product, and We have the identity now. Okay, so part 2 is actually an application of part 1. Okay, combining with the result in proposition 7.2.8. Okay. Okay, now, once we have proved proposition 7.2.b, all right, for two independent random variables, x and y, okay, we can now extend the result to two independent collections of random variables. So we have X collection, suppose we have and the Y collection with two independent collections of random variables. Now assume that we have two data processing functions. One is for the X collections. And these two data processing functions are Borel and measurable. Real valued function. On Rn and Rm respectively. Okay. Then the proposition 6.2.j says that then the data processed result g of x1, x2 up to xn, and h of y1, y2 up to ym are independent random variables. Okay, so that is the proposition 6.2.j. And so that this, combining this proposition, we have proposition 7.2.c. So let x1, x2 up to xn, and y1, y2 up to ym be two independent collections of random variables, and assume that g of x1, x2 up to xn, and h of y1, y2 up to ym are Borel measurable real valued functions on Rn and Rm respectively. Okay, so now the first statement, if G and H are non-negative. Okay, so if the values of G and H are non-negative, then the expectation of G of x1, x2 of xn terms with h of h y1, y2 up to ym. Okay, so the expectation of their products is equal to the product of their expectations. Okay. Okay. The reason is because that this new random variable and also this new random variables are non-negative random variables. So we can apply part 1 of proposition 7.2.b. Okay. The second, if G of x1, x2 up to xn and h of y1, y2 up to ym have finite expectations. Okay, then their product all right, so their product has a finite expectation. And this expectation okay, so the expectation of their product is equal to the product of their expectations. Okay, so expectation of G of xi times expectation of H of y j's. Okay. Okay. So that is the direct result of proposition 7.2.b. All right. Now, we'll. So in some situations, we will deal with question about the serious sum of an infinite sequence of random variables, x1, x2, etc. All right, so we first assume that for each outcome omega in the sample space, yes, the series x omega we defined to be which is the limit of the partial sum, okay, exists. Okay, so we assume that. So for each outcome, okay, this is series sum because for a given outcome, this is a numerical value, real numbers, and so we assume that this is series sum of real numbers defined to be this one exist, okay, and it can be shown that x. So now x defines a function, okay, a real value function on the sample space, and this one is a random variable. Okay, so it can be shown, but we will omit the detailed proof for that. Okay, so this is indeed. Now the question is that so the next question is that does the expectation of the series sum exist? Okay, so we have usually have these questions, and if exists, okay, how to compute it? Right, so we know that the expectation of x so this is the limit okay. So the question is that can we exchange the order of expectation and the limiting process? So by the limit, so this is from the linearity. Okay. So this is a series sum. Okay, so we ask for the condition under these conditions that we have the equality here, okay, which means that we can exchange the order of expectation and then the limiting process. Okay. Now there are two conditions, all right, each of which guarantee the equality. The first is that all x sub I are non-negative random variables. So if xi's are non-negative random variables, then it's quite natural that we can exchange the order of expectation limit. Okay? And for non-negative random variables, we know their expectations always exist. Okay? Right, so there is no question about them. Okay? So if they are non-negatives, so non-negative random variables actually are very, I say adorable, okay, lovely, but because they are so nice to deal with, okay. Now, the second condition is that the expectation of, all right, so that this is serious sum, okay, which means that each x sub I has finite expectation, all right, and the serious sum of the expectation of their absolute value is finite. Okay. Right. So if x sub i's are general random variables, okay, maybe positive valued, negative value, or zero valued. To guarantee that this is true, okay, is to guarantee that the expectation of their absolute value has a serious sum which is finite. Okay? So the check-in, the check-in of the condition is very simple, right, for you. Okay, so under either one, okay, or one first condition or in second condition, you are guaranteed to have the identity here. Okay? So this is a very nice property for you to do it. All right? So any questions? All right, so we have developed quite a few fundamental properties of expectations of functions of random variables, right? Okay, and section 7.3 is actually an application of these properties. Okay, so moments of the number of events, okay, that occur all right, so the topic seems simple, but has various applications. Okay, so in many problems, you can reduce the statement into a certain form such that this concept can be applied. Okay, all right. So let's A sub I be events of interest in our selected sigma h by f, and let I sub I be the indicator, okay, of the event AI. I believe you know what is indicator of an event, all right? But if you forget, right? So indicator is a 0, 1 value, a random variable. All right. So it's the indicator to show whether an outcome is in a specific event AI. Okay. If the outcome is in AI, then the indicator has value 1. But if the outcome omega is not in AI, then the indicator has value 0. Okay. Okay. So from that we know that AI is actually the event that equal to 1. Okay. Okay. So these two events are the same. And the probability of A sub I is equal to the expectation of II. Okay, we know that. So probabilities, any statistical properties of an event can be deduced from its indicators. Okay, so statement about an event AI, okay, can be restated in terms of its indicator. So indicator has the same, the same information of the event itself. Okay, now define a new random variable. So the new random value is the sum of these n indicators. Okay, right? So it's a function of n random variables, right? And because the summation, the data processing function, the summation is continuous function, so it's Borel measurable. So of course, x is a random variable, of course. Okay, it's a random variable. So now, so x is the number of these events that occur. All right. So if we want to know that for each outcome omega, okay. So if the outcome of a random experiment is omega, we want to know that the number of events that occur. Okay. And whose expectation? Sorry, I didn't turn it off. Okay, so whose expectation is now by linearity of expectation. So that this expectation it becomes to be the summation of the probability of each event A sub I. Okay. So this is quite simple, right? To find the expectation of the number of events that occur. Now we can deal with a more complicated problem. The next is the number of pairs of events that occur. Right? All right, so the number of that occur would be okay, so it's X select 2. Right, because if for certain outcome omega, the number of events that occur is X of omega. Suppose X of omega is 3. Right? So in these 3 events, we have 3 pairs, right? Because 3 is select 2. So we have 3 pairs. If for a certain outcome omega, the number of events that occur is 5. Then the number of pairs would be 5 selected 2. So that would be 10, right? So we have 10 pairs. All right, so the number of pairs of events that occur would be this number. All right, so which is, so what is that? So it is equal to but a simple one would be here, expressed okay by the product. So we consider all possible pairs. Okay, we consider all possible pair, ij, so that the pair occur if and only if the product is equal to 1. Okay, and so the summation means that the number of pairs that occur. Okay, so you can do that, right? Divide by 2. So that is one expression. But a better expression would be by using the indicator, so that you're using the product. Okay, and here we restrict that because the pair we want to use the unique pair, so we require I is less than j. Okay, so this sum consists of so that this is a sum with n terms. Okay, so we have that many terms here. We have that many terms. Okay, so you can either do this, okay, or that. But in this case, if you want to compute its expectations, then you have to consider the second moment, right? Okay? So you have to consider the second moment. But in here, the expectation will be quite simple. And whose expectation is here. So this is become to be the expectation of this one. And so that it, the probability that AI intersect AJ. Okay, since expectation of Ij is equal to summation of is equal to 0 times probability that Ij equal to 0 plus 1 times probability Ij equal to 1. Okay? But this is I1 is equal to 1. This is equal to the product is equal to 1, but that is equal to okay? And we know I equal to 1 is AI, so this is probability of AI, in this case AJ. Right? So this expectation is equal to the sum, okay, of the probability of AI and AJ. Okay, and here they have n terms. Okay. Any questions about the expectations? Okay, and now we know this is expectation of okay. So combining these two identities, we can find the second moment of X. So we know that okay, so that's the second moment is equal to the first moment times 2 okay. Okay, and this one, probability of AI, plus 2 so now, so this is become 2. Okay, so this is become 2, the ij from 1 to n. Or you can express by the double sum. Okay. So it is actually, this is a surprising result, right? Okay. So I and j can be independently be assigned an integer of an index from 1 to n. Okay, so this is double sum of this joint probability. Okay, so that this is expectation of 2 here. Any questions up to now? In general, the number of distinct subset of k events that all occur is equal to x select k. Okay, and this can be I1 less than I2 less than I sub k less than n, and I sub I1, I sub I2, I sub ik, the product of them. Okay, so it's the sum of n stack k terms. Okay, so we have not many terms there. And we know this is quite complicated, right? Okay, so this is this expression here. And whose expectation okay, So this is the summation. The probability that I sub 1 intersect I sub 2 intersect A sub I sub K. Okay, so in principle, so with the expectation of xk, we can compute all the moments of x for k from 1, 2, 3, etc. So a question for you. Right. So try to find. Okay. If you want to prove that, you can use that. Prove that by induction. You can see that the expectation of x, the first moment is just the probability of a single event, AI, and sum over all possible this event. For the second moment, you see that it is the summation of all possible joint events, AI and AJ, right? And for all possible I and for all possible J. There are no restriction on I and J. They're just from 1 to n here. Okay. So if you can have a good conjecture, right? What is the simple formula for the case moment? You can conjecture that, and you can prove that by induction. Okay. All right. So let's take a break up to 2:35. Okay. All right. In the proof of part 2 of proposition 722.B, I forgot to mention the point. We let G plus so it is clear G plus and G minus are continuous function. On R. And then Borel measurable. Okay, so they are Borel measurable function. Now, since x and y are independent, okay, since they are independent, so x plus, which is g plus of x, and y plus, which is g plus of y, are independent. So they are independent non-negative random variables. X plus and y minus, which is g minus y, are independent. X minus y plus independent, and x minus y minus are also independent. Okay? So x plus, y plus are independent non-negative random variables. Okay? So that this is the reason why we can apply part 1. Okay? Because to apply part 1, we need 2 independent non-negative random variables. Okay? So I forgot to mention that the part 1 and part 2, positive part and the negative parts, they are functions of respective random variables. Okay, okay. So actually, we have a positive part by doing the data processing. Okay. Similarly, we do the for the negative part, we do the another data processing. Okay, so you can see what is. So this is g plus of x. Okay, so that is g minus of x. Okay, so you can see both of them are continuous functions. Okay. This is actually a rectifier, right? In the circuit theory. Okay, and this one x related to rectifier, but it's a variant of the rectifier. Okay, so you need this, I forgot to mention in the proof of the second part of proposition 7.2.b. Okay, so we finish sections 7.3. Now we go to section 7.4. We will talk about covariance, variance sum, and correlation coefficient. Okay. Okay, before we adjust formulas for this concept, we define a new concept here. Two random variables, x and y, are called equal with probability 1. With probability 1, okay? As abbreviated with W.P.1. If the probability of the event that x equal to 1 is equal to 1. Okay? So this event so that is the probability that equal to 1. Okay? And this event we define to be delta omega. Okay? So if there exists an event omega in the sigma algebra F with the probability of omega 0 is 1, such that S omega equal to okay. Right? So x equal to y is this event. Okay, is the set of all outcome omega such that x of omega equal to y of omega. Okay, and this is an event. Okay, we call it omega 0, and this event occurs with probability 1. Okay, so we say two random variables are equal with probability 1 if even only if that they are equal So the event that x equal to y occurs with probability 1. All right, and so we can state it the other way, that there exists an event omega 0 with probability 1, such that for all outcome in this event, these two values are equal. Okay, so you have quite a couple of different expressions to illustrate the same concept. Okay. Okay. Now we will so how to categorize that two random variables are equal with probability 1? All right, so we will categorize this concept in this proposition. If two random variables, x and y, are equal with probability 1, then these two events, x in a parameter B has probability equal to the probability that y is in B. Okay. For any real set B in R. Okay. So statistics, so two random variables are equal with probability 1 can be identified as the same random variable in terms of probabilities, in terms of this way. Okay, so that because this is all the event that can be described by a random variable, right? So we discussed that any event involving a random variable is described in this way. It says that x random variable has value in a certain Borel set. Okay, so and so you can see that to describe the event in this way is the same as to describe the event in this way, because they have the same probabilities. Okay, so the proof here. Now, since this event intersect, so we let omega 0 to be the event that x equal to y. Okay, so we know that omega 0 occurs with probability 1. And the probability of the complement of omega 0 is 0. Okay. All right, so this is the case. Now, since if we consider that the intersection of this event with the complement omega 0, and we know that this probability is less than or equal to the probability of the complement omega 0. Okay? And this is 0. Right? So that, which by the sandwich property, then this probability is 0. Okay? The same as y in B. In the set omega 0 complement. Okay. So this shows that. So by the sandwich, so that this becomes to 0. So this is 0 probability. So we have, so now the probability that X in B, okay, now by the decomposition formula, intersect omega 0 plus probability that X in B intersect omega 0 complement. Right? Since the total event is equal to the disjoint union of that. So this is actually the decomposition formula we have described in chapter 3. Okay, so we have that. But this probability is 0, right? As we have just shown. Okay, so this is equal to the probability. Okay, so here, because this probability is equal to 0. Okay, so we have that. Okay, but this joint event is equal to probability that y in B in the cell. Why? Since if we have an outcome in this joint event, which means that X omega is in B and omega is in omega 0. Right? But if outcome omega is in omega 0, X omega is equal to Y omega. Right? Is that clear? Because by our definition, omega 0 contains all outcomes such that we have this equality. Okay, so omega in here and there's equal. So this means that omega is in. Okay, so actually these two events are the same. Is that okay? Okay, and okay, plus probability The reason is that this probability is equal to 0. Okay, and this is probability that Y in B. Okay, and so we have done. Okay, so if two random variables are equal with probability 1, then we have this equality for any Borel set B. Okay, so we can make a couple of remarks. First one, if x equal to y with probability 1, then if we look at the CDF of x, this function is probability that x less than equal to little x, okay? And the probability of this event is same as the probability of this event. All right, so this is by proposition 7.4.8 with the Borel set, which is equal to this interval. Okay, and so we have f of y. Okay, so if two random variables are equal with probability 1, then they have the same cumulative distribution function. So their CDFs are the same, are exactly the same function. Okay, so that they have the same. Okay, so they have the same distribution. Second one, if x equal to y with probability 1, then they have the same expectation if any of exists. Okay, so if one random variable x, for example, if x has expectation here of x, then EY exists too, and they are equal. Okay. The reason is because they have the same distribution, right? Because this the distribution determines expectations. Now, a random variable x is called no less than another random variable y if with probability 1 if the event that x greater than equal to y, right? So no less than means x greater than equal to. This event has probability equal to 1. Okay, so this is saying that the probability of this event is equal to 1. And so again, we let this to be omega 0. So another description is that if there exists an event omega 0 in the sigma algebra with probability 1 such that for those outcome in omega 0, we have this inequality. Okay. So remark, in this case, i.e. x greater than or equal to y with probability 1, if we define z to be the difference, right? So z is, so this one has greater than or equal to 0 for all omega in omega 0. Okay? Which says that z greater than or equal to 0 with probability 1. Okay? Right? So if x greater than y with probability 1, if we define z to be the difference, then z will be non-negative with probability 1. Which means that, so by defining a random variable, so now we define a random variable C prime right? So we define a new random variable okay, then z prime is a non-negative random variable, and z equal to z prime with probability 1. Okay. Okay, so z is non-negative with probability 1 means that z is equal to a non-negative random variable with probability 1. Okay, so that expectation of z is equal to expectation of z prime and is non-negative. Okay, by remark 2 after dash 2 after proposition 7.4.8. Here, okay. So if two random variables with probability 1, and if one of these two expectations exists, then they must be equal. Okay, so we have that. Any questions? Okay, so this discussion is used to clarify some concept that will be used later quite often. For example, Z is non-negative with probability 1. What is the meaning of that? Which means that Z is equal to a non-negative random variable with probability 1. Okay, and how to construct such a non-negative random variable? Well, this by this way. Okay, so because it's non-negative means that Z omega is non-negative for all omega for all outcome in the capital omega 0. Okay, and this event occur with probability 1. All right, so now if x and y are two random variables with x greater than or equal to y with probability 1. Okay. Oh, lit. Sorry. Okay, so with that, we have two random variables, and we know x greater than or equal to y with probability 1. Now, first of all, if x and y are non-negative, then the expectation of x is greater than or equal to expectation y. Okay? Second, if expectation of x exists and is finite, then expectation of y exists and is finite, and we have the inequality for their expectations. Okay. It's very intuitive, right? To say that if x greater than or equal to y with probability 1, then their expectation will have the same inequality, right? This is a very intuitive idea, but to state it precisely, you have to give different versions. If x and y are non-negative, of course, this is no problem. Okay, it's no problem because the existence of these two expectations, because they exist and non-negative. Okay, and we have this inequality. But if x and y, if at least one of them is not non-negative, then we will have to go to the second statement. So we have to know that the expectation of x exists and is finite. Okay? In this case, then, because y is less than or equal to x with probability 1, so y has expectation, right? So the expectation of y exists and is also finite, and then we have this inequality. Okay. Okay, now since x greater than equal to y with probability 1. All right, so there is an event omega 0 in the sigma algebra with the probability of big omega 0 equal to 1, such that all right, we have this inequality for all outcome in omega 0. Okay. Now, and then let z to be the difference. Then we know z is greater than equal to 0 with probability 1, and expectation of z is non-negative by the discussion. So by the remark up here and above. Okay, so by this remark here. Okay, now the first case is that x and y are non-negative. Okay. Now x is equal to x minus y plus y. So this is z plus y. All right. So x is the sum of z plus y, sum of z and y, and both z and y are non-negative random variables with probability 1. So we have the linearity okay, by the linearity of expectation in proposition 7.2.a. Okay. Even though in the statement of proposition 7.2.a, we say that x and y are negative random variables, but it's the same, all right? The same if they are non-negative with probability 1. Why? Because we can find z prime and y prime, right? So z equal to z prime, y equal to y prime with probability 1. And the z prime, y prime are non-negative random variables, as we discussed before here. Okay. And then, so expectation of z and expectation will be the same of expectation of z prime. Expectation of y is the same as expectation of y prime. Okay. So the replacement will be quite easy, right? So z prime y, okay, and z plus y corresponding to okay. So you can see with probability 1. Okay. Okay, and here, so here, so this is these two non-negative random variables. Okay, so we say Z and Y are non-negative with probability 1, means that Z equal to a non-negative random variable with probability 1, Y is equal to a non-negative random variable with probability 1, and so that their sum is equal to this sum with probability 1. And in here, because Z prime, Y prime are non-negative, so we can apply the linearity of expectation, right? And so here we will have, so now, okay, but this is equal to Y, because Z plus Y is equal to Z prime plus Y prime with probability 1. Okay, and so this is, okay, so again, you get the same linearity. Okay, so everything about the expectation of something related to the distributions, they can apply to situation with probability 1. Okay, so when we apply proposition, so the linearity of expectation, then we will have the same formula. Okay, and so this is greater than or equal to expectation Y, of course. Okay, since expectation of Z is greater than or equal to 0. Okay, so that is the part 1. That is part 1 here. Okay, so now I have to stop here. So for part 2, we will continue the discussion. We'll come in Thursday. Sorry.